When it comes to discussing open systems, we talk about control volumes. So control volume is a region of space that we are considering for the given problem. Since mass is a conserved property, that means mass cannot be destructed or created. For any system, mass conservation is applicable. That means mass came in minus mass went out should be equal to mass change within the system. But here we are discussing about steady flow systems. In a steady flow system, because the system is steady, that means the properties in the system doesn't change, we have to consider that the mass change within the system is equal to 0. So for a steady state system, mass came into the system is equal to mass went out of the system. However, you have to remember that for a steady flow system, volume came into the system is equal to volume went out of the system only if the system's fluid is an incompressible substance. For an example, liquid is an incompressible substance. So the volume change with pressure is negligible. Density doesn't change. So mass conservation gives us the volume came in is equal to volume went out. But remember, there is no concept called volume conservation. Volume came into the system will be different from volume went out of the system if the fluid is compressible. When we are applying energy balance for an open system, the difference between our closed systems that we already studied is we have this mass into energy of the flows came in and flows went out. So energy came into the system with the flow have three components according to this equation: enthalpy, kinetic energy of the flow, potential energy of the flow are those three components. Remember, this kinetic energy is different from the kinetic energy of the system, and also potential energy is different from the potential energy of the system. The right hand side of our energy balance equation shows the energies within the system. So the kinetic energy and potential energy shown here only becomes non-zero if the system itself is moving. Most of the systems that we are going to consider are going to be stationary systems, or we can assume they are stationary. So we can neglect this part. And almost all the systems that we are going to consider is going to be steady state. For a steady state system, properties within the system does not change. So the internal energy change of the system is going to be 0. So the right hand side of the equation is going to be 0 for any steady stationary system. In addition, most of the systems that we are going to consider are going to be small systems. So they are going to be something like a turbine, a compressor, but not something like a hydroelectric power plant. In that case, because the inlet and outlet are close together, we can consider that the potential energy difference between the inlet and outlet are negligible. And remember, this Q given in this energy balance equation represents energy flows that crosses the system boundary due to temperature difference, and W represents energy flows that crosses the system boundary due to forces other than temperature difference. So W can be electrical energy, shaft energy, spring work, etc. One thing that I want to mention here is flow work. Flow work is very similar to boundary work that we discussed in closed systems. You can imagine that the flow work is the work that is necessary to keep the system's flow flowing. We can imagine that the system's inlet has a piston and cylinder device to push the fluid into the system. In that case, we can write that the work done to push this fluid into the system is equal to PV. This is called flow work, but we are not going to show this in our energy balance equation because enthalpy contains this flow work. If you can remember, in chapter 3 we defined enthalpy as internal energy plus PV. So flow work is integrated into enthalpy of the fluid flow.